Interfet, the world's largest supplier of JFETs. In this video, we will develop a switched feedback transimpedance amplifier for use in typical sensor applications. For this design, we'll be using QSpice to draw and simulate a circuit. The circuit will use an op-amp and several JFETs to create a transimpedance amplifier with controllable gain. We will need some power supplies to begin with. We'll use plus and minus 15 volts for the op-amp supply, and we will use minus 3.3 volts for the gate supply for the JFETs. The basic circuit will be an inverting amplifier with a large feedback resistor, in this case 100 gigohms. The input signal will be a very small current, like that which is produced from a photodiode. When exposed to light, a photodiode will output a small current signal. Here we will use a current source to represent the photodiode. We will configure the current source to produce a 210 picoamp sine wave at 1 kHz with 983 picoamps of DC current. If we perform a transient analysis for 1 full second, we see that the output is a sine wave with an amplitude of about 12 volts peak to peak. When we zoom in, we can see that the sine wave shows no obvious distortion. Our goal is to now use a digital input and change the gain of the circuit. One method to change the gain is to add another resistor in parallel with the 100 gigohm feedback resistor. We can use a JFET as a switch to place this second resistor in or out of the circuit. Since the N-channel JFET needs a negative signal on the gate to turn it off, we will use a resistor to pull the gate to minus 3.3 volts. That will turn the JFET off. We can add a pulse voltage source to emulate a microcontroller digital output. The pulse will be from 0 volts to 3.3 volts. It will start at t equals 200 milliseconds. It will have a rise time and a fall time of 500 nanoseconds and will last 100 milliseconds. We can see a simulation of the control pulse that shows that. When V4 puts out 0 volts, the JFET gate is at about negative 1.65 volts and the JFET does not conduct, and R6 does not affect the feedback circuit. When V4 puts out a positive 3.3 volts, the gate of J1 goes to 0 and the JFET turns on and R6 is in the feedback circuit. The effective feedback resistance is now the parallel combination of R4 and R6. So instead of 100 gigohms, the feedback resistance is now 9.09 gigohms. If we run the simulation again, we see that the overall gain is reduced when JFET switch J1 is on. We can repeat this circuit with a different feedback resistor for another gain setting. Note that R8 is different from R4 and R6. We can even add another stage with yet a different feedback resistor. Note that the pulse control for the two new channels are different, with V5 coming on at t equals 500 milliseconds and V6 coming on at t equals 800 milliseconds. The control pulses are simulated here. They will produce a simulation of the final circuit as shown here. We can identify 3 regions where the gain is reduced by the lower feedback resistance that is switched in, and we can see 4 places where the gain is at the level caused by the 100 gigohm resistor. Note that there is a transient in the signal when the switches are turned on or off. Charge injection is causing the output to spike to the power rails. This problem may not be an issue for some applications and will likely increase cost and complexity to solve. If we choose to activate 2 of the control pulses at the same time, or even all 3, we can create a total of 8 different gains as shown in this table. In summary, we have seen how JFETs can be used as switch elements in a transimpedance amplifier.